Hello student, how are you all? I hope you all are doing good. I am Pooja Tripathi, your teacher. So student, we have learned about the exponent and power in the previous class also. In this chapter, we are going to learn all this in details, what are the different rules, what are the laws, how can we find out exponent, what is the power, all this we are going to learn in this chapter, exponent and power. Our learning objectives are introduction to exponent, laws of exponent, counting, combination, the other side of the exponent, negative powers, application of exponent, estimation or approximation, qualifying the word with the power of 10. So we are going to start with the introduction to exponent. In the earlier classes, we have learned that some quantities do not increase by adding the same amount each time. Instead, they grow much faster because they are multiplied repeatedly. For example, a certain types of algae in the pond might be double in the number every hour instead of increasing by just a few organisms. This kind of rapid repeated multiplication, that is called exponential growth. This is called exponential growth. To express such repeated multiplication, neatly mathematicians introduced the convention and the compact method. That method is known as exponential notation. Now, why use exponent? Writing the multiplication like 3 multiplied by 3 multiplied by 3 multiplied by 3 again and again, that become lengthy. Using the exponent, we can shorten it as 3 is to power 4, which we read as 3 raised to the power 4. Now, part of an exponential expression. Take the example 3 is to power 4. Here 3 is the base. This is the number that repeatedly multiply. Now, exponent, if we talk about the exponent, here the exponent is 4. This tells us how many times the base is multiplied by itself. Power 3 is to power 4. This entire expression represent one power and its value 3 is to power 4. 3 into 3 into 3 into 3, that is equals to 81. Now, general form, if the number a is multiplied by itself m time, we can write a multiplied by a multiplied by a m time, we can write a is to power m. Here a is the base, m is the exponent and a is to power m called a power. Where can exponent be used? Now we will learn where we can use these exponents. Exponent can be applied to whole numbers, positive and negative numbers, fraction and decimal. All these cases we can use exponent. The rules remain the same. The base is multiplied by itself as many times as the exponent indicate. Thus, the exponential notation gives us the simple yet powerful way to represent repeated multiplication, especially in the situation involving rapid growth or very large or very small number. Here we will take an example. Here write the following expression using exponent. P multiplied by P multiplied by 4 times multiplied by Q multiplied by Q 4 times. So the solution is P appear 4 times. So P here is base and the exponent is 4. So P is to power 4 and Q appear 4 times. So it become Q is to power 4. So therefore, the expression in the exponential form is P is to power 4 multiplied Q is to power 4. Now, here we will take one more example. Express each number as the product of prime factors using exponent. 720. So prime factorization of 720 is 2 into 2 into 2 into 2 into 3 into 3 into 5. So exponential form 2 is to power 4, 1, 2, 3, 4, 3 is to power 2 multiplied by 5. This is how we are going to write. Next, laws of exponent. Now that we know how exponent help us to write the repeated multiplication in the compact way, the next step to understand how to operate with these expression. For example, 12 is to power 5 multiplied by 12 is to power 8. Without the exponent rule, we would have to write 5 12s. So if we don't know the rules, what we are going to do? We will write 12 5 times, then 8 and then 8 more. 12s which be long, that would be very long. 12 multiplied by 5 times, then 8 times, and which would be long and unnecessary. This defeats the purpose of using exponent as a shortcut. So how we are going to use this? Now, to make such calculation easier, mathematicians provide the set of guideline laws of exponent. These rules act as a special tool that help us to multiply power, divide power, simplify expression and handle the same base raised to the different exponent. The laws gives us clear principle. Now, explaining how exponent behave in a different situation, with these rules we can deal with even very large or very small numbers efficiently and accurately. Product rule. What do we do when we multiply two exponent and expression that share the same base? If the base is same, let's examine 7 is to power 4 multiplied by 7 is to power 3. Here the base is same, 7. So writing each power expanded form, this is like this. Now combining all factor, will get 7 is to power 7. So notice the exponent 7 is obtained by adding the original exponent 4 and 3. So this observation gives us a very important law. When two powers have the same base, if the base are same and are multiplied, their exponent are added. We will add the exponent. General rule for any non-zero base is a and any integer m and n. A is to power m in multiply by a is to power n. Here we are multiplying, the base is same, so we will add the power. A is to power m plus n. This rule allows us to simply expression quickly without writing out long repeated multiplication. Now, we will take an example here. Simplify m is to power 5 multiply m is to power 7. Now, both the terms have the same base, that is m. So, according to the product rule of exponent, when the power of the same base are multiplied, if the base are same and they are multiplied, we will add their exponent. So, m is to power 5 plus 7, m is to power 12. Thus, the simplified form of expression is m is to power 12. Now, quotient law of power. After understanding how power behave during multiplication, let us now examine what happened during the division. Division is the opposite of multiplication. Division is the opposite of multiplication, so the way exponent behave also follow the different pattern. Understanding through an example. Let us take an expression. So, expression is 4 is to power 7 divided by 4 is to power 3. So, understand better, we will write this in expanded form. Now, place the term in a single fraction. 4 is to power 7 divided by 4 is to power 3. Cancel out the common terms. So, we will get 4 is to power 4. 1, 2, 3, 4. So, we are left with 4. 7 minus 3. So, notice that 4 that is equals to 7 minus 3. This shows when two powers with the same base are divided, we will subtract the exponent if the base is same and there is division. Then what we are going to do? We are going to subtract the powers or the exponent of the numerator. Clear? Now, general exponent rule for division for any non-zero base a and for the integer p and q. Meaning of the rule: division of power is only possible directly when the base is identical. Base should be same. The base remain the same in the result. The exponent in the answer is obtained by subtracting the exponent of the lower part, means denominator, from that of the upper part, means from numerator. Take an example here. simplify the power of expression using the quotient law. So let us consider the expression 9 is to the power 10 divided by 9 is to the power 4. So step by step solution, both the terms have the same base are same, 9, which is 9. According to quotient of law exponent, when two powers have the same base and divided, we subtract the exponent in the denominator from the exponent in numerator. So 9 is to the power 10 minus 4. Now, thus the simplified form, that is equals to 9 is to the power 6. Exponent on the expression inside brackets. We have learned how to combine powers that have the same base by adding exponent when multiplying and subtracting exponent when dividing. When the power is applied to the number or expression enclosed in bracket, the exponent acts as every factor inside the bracket. This leads to another important rule of exponent. This we will explore next. Now, the powers of a power rule. Sometimes we come across expression where an exponent is raised to another exponent. So, in such situation, we need to understand how two exponents interact. Example, to understand the concept, consider the expression 5 is to power 4 and whole power 3. This means the power is being multiplied by itself 3 times. The power is multiplied by itself 3 times, means 5 multiplied by 4 multiplied by 5 is to power 4 multiplied by 5 is to power 4. Now we'll apply the product law of exponent, which tells us that when we multiply power with the same base, we add their exponent. Like 5 is to power 4 plus 4 plus 4 plus 4, that is 12. Note that 4 into 3, that is 12. It shows the easier way to evaluate the expression. When the power is raised to another power, we multiply the exponent, that is now the general rule for any non-zero base a and the integer m and n. A is to power m multiplied by whole power n. So that is equals to a is to power m multiplied by n. This rule also be written as a is to power n whole power m, a is to power n m. Both forms shows that the order of the multiplicand does not change the result since the multiplication is commutative. We know multiplication is a commutative property. We can multiply two or more number in any order. Example, simplify the power raised to another power. Let us simplify the expression 3 is to power 7 whole power 4. Solution, this expression shows that the power being raised to another power according to the power or the power rule. When this happens, we multiply the two exponent. So 3 is to power 7 multiplied by 4, 3 is to power 7 into 4, that is 3 is to power 28. Clear? So we have learned how to work with the powers that had the same base. If the base is same, whether we multiply them, divide them or raise one power to another, that we have learned here. When the exponent is placed outside the bracket, it applies for every factor inside the bracket. This leads to the another important rule involving the power of the product and expression, which we will explore next. That is power of the product rule. Sometimes the entire product is raised to the exponent. In such expression, the exponent does not act as the product of the whole only. It applies each factor inside the bracket. We'll take an example here to understand this. Example, to understand this rule, consider the expression 2 into 5 is to power 3. So we understand what it means. Expand it and repeat the multiplication. So this is how we are going to expand it. 2 into 5 multiply by it 3 times. Now regroup like the factor. So 2 into 2 into 2 multiply by 5 into 5 into 5. So that is equals to 2 is to power 3 multiply by 5 is to power 3. This shows that the exponent 3 was applied separately in both the factors inside the bracket. When the product is raised to the power, each factor of the product receive the same exponent. Now the general rule for any non-zero number a and b and any integer a into b whole power n. So that is equals to a is to power n multiplied by b is to power n. This is known as the power of the product rule. So here we will take an example. Simplify the expression 7c is to power 4. Solution: the expression 7c is to power 4 shows that the product 7 multiplied by c being raised to an exponent. So according to power of the product rule, the exponent must apply the each factor inside the bracket. So we will distribute the exponent 4 to both 7 and c. So that is equals to 7 is to power 4 multiplied by c is to power 4. Now evaluate the numerical power. 7 is to power 4, that is equals to 2401. Thus the simplified form, that is 2401 c is to power 4. Next is power of quotient rule. Just as we applied the exponent to each factors of the product, we can also apply an exponent to each part of the fraction when a quotient is raised to the power. The exponent affect the both numerator and denominator. Let's see example to understand this rule. Consider the expression 3 by 8 is to power 4. So see, this means the expand it as the repeated multiplication. So we will expand it like this. Now multiply all the numerators together and all the denominator together. That is equals to 3 is to power 4 upon 8 is to power 4. This shows that exponent 4 has been applied separately for both the numerator and the denominator. Now key idea. When the fraction is raised to the power, the exponent apply both the top number means numerator and the bottom number, that is numerator. Now the general rule. For any non-zero b, any number a and any integer n, a upon b is to power n, that is equals to a is to power n upon b is to power n. Here b is not equals to 0. This is known as the power of the quotient rule. Let's see some examples. Simplify 4 by 7 is to power 3. So to simplify the expression, we will use the power of quotient rule, which tells us that when the fraction is raised to any exponent, the power must be applied to both the numerator and the denominator separately. The rule can be written as a upon b is to power m. So the power n is for a and b both separately. So that is equals to a is to power n upon b is to power n. In this example, the numerator is 4 and the denominator is 7 and the exponent is 3. So we must raise both 4 and 7 to the power of 3. 4 upon 7 whole power 3, that is equals to 4 is to power 3 upon 7 is to power 3. Now evaluate each power step by step. 4 is to power 3 means 4 multiplied by 4 multiplied by 4, that is equals to 64. 7 is to power 3 means 343. Now putting this value together will get 64 upon 343. Thus the simplest form of the expression is 64 upon 343. The zero exponent rule. Let's now investigate what happens when the exponent becomes 0. What if the exponent becomes 0? Consider the expression 12 is to power 5 divided by 12 is to power 5. We know from the basic arithmetic that any non-zero number divided by itself, that is equals to 1. If we divide any non-zero number with itself, we will get 1 as a quotient. So 12 is to power 5 divided by 12 is to power 5, that is equals to 1. Now, by comparing the two results, we will reach an important conclusion. 12 is to power 0, that is equals to 1. That leads to zero exponent rule. X is to power 0, that is equals to 1. Here x is not equals to 0. The condition x is not equals to 0 is essential. Our reasoning really relies on the division. The division by 0 is undefined in mathematics. Therefore, 0 is to power 0, that is not defined. Let's take an example here. Simplify the following expression. 3 is to power 4 multiplied by 3 is to power 5 divided by 3 is to power 6. Now step 1, use the product rule. First we'll use the product rule because here we have to multiply. 3 is to power 4 multiply 3 is to power 5, that is equals to, base is same according to product rule, base is same, the power is added. 3 is to power 4 plus 5, that is 3 is to power 9. Now apply the quotient rule. 3 is to power 9 upon 3 is to power 6. Here base is same. If we divide, the exponent get subtracted. So 3 is to power 9 minus 6, 3 is to power 3. So answer is 3 is to power 3. You have to practice all the examples given here. Next is learning point 2.1. All these questions are for your practice. Practice all the questions given here. Next is counting combination. Think of this scenario. You have 3 different shirts. One is yellow, why for yellow? One is grey and a pink shirt. And the 2 pairs of pants, that is black and brown. Now the shirt, Y means yellow, G means grey and P means pink. And pants, B, that is black, and BR, that is for brown. Now figure out all the possible outfits. We pair each shirts with each pair of pants. The total number of combination can be calculated by multiplying the number of choices of shirt with the number of choices of pant. So total outfit, 3 shirts and 2 pants, 6. So the possible outfit combination, YB means yellow shirt, black pant, yellow shirt, brown pant, grey shirt, black pant, grey shirt, brown pant, pink shirt and black pant, and pink shirt and brown pant. Whenever multiples independent choices are made after another, the total number of possible outcome is found by multiplying the number of options available in each step. For example, making sandwiches. Suppose you want to make sandwiches and there are 4 types of bread: white, wheat, multigrain and rye. Okay? And 5 types of filling, that is cheese, lettuce, tomato and chicken, and egg. If you choose 1 bread and 1 filling for each sandwich, how many different sandwiches you can make? Number of bread available, that is 4, and number of filling option, that are 5. So total number of sandwich combination possible are 4 into 5, 20. So you could create 20 unique sandwiches mixing and matching different breads and filling. Now we'll take an example here, creating a security code. Imagine a security code that consists of 2 letters followed by 2 numbers. First 2 letters and then 2 numbers. The letters can be chosen from the alphabet A to Z and the number can be selected from 0 to 9. In this case, the repetition is allowed, meaning the same letter or the number can be a pair more than 1. So what are the steps? Count the choices of letter. Choices of first letter A to Z, there are 26 alphabet, and choices of second letter are again 26 A to Z. Count the choices of number. Choice of first number 10, 0 to 9, and choice of a second number again 10, 0 to 9. Now multiply the choices. So there are 67,600 unique security code possible with this system. So total possibility 26 into 26 into 10 into 10, 67,600. Next is expanded explanation. The reason we multiply is that each step is independent. The choice of the first letter does not affect the second letter, and the choice of the number does not affect the other number. This is an application of the fundamental counting principle, which state if there are multiple independent stages in an activity, the total number of outcome is the product of the number of choices at each step. Fundamental principle of the counting. The fundamental principle of the counting help us to determine the total number of possible outcome. They help us to find the total number of possible outcome when there are multiple independent choice to make. Suppose the first choice can be made in different ways. Suppose the second choice can be made in B different ways. Then the total number of ways to make that is equals to both choices A into B. Similarly, if there are 3 independent n choices with A, B and C option respectively, the total number of possible outcome that is equals to A into B into C. Now, important rule, each choices must be independent, meaning the outcome of one choice does not affect the option on for the next choice. For the sequence of k independent tasks, there are number of option in each task is n1 into n2 into n3 till nk. Total number of ways that is equals to n1 multiplied by n2 multiplied by n3 and nk. Note, sometimes the problem include restrictions on one or more choices. Sometimes there are restrictions also. We will use the fundamental principle of counting, but we must carefully count the option for the restricted event. So, here the example of creating a 5-digit security code. Suppose 5-digit security code must start with a digit from 2 to 7. So, start with digit 2 to 7 and the remaining 4 digit can be any number from 0 to 1. Starting 2 to 7 and remaining number could be any digit from 0 to 9. Now, how many different codes can we form? Solution. Number of choices for the first digit, that is 6. Because any digit from 2 to 7 and number of choices for each of the remaining 4 digits, that is 10, number 0 to 9. So, total codes 6 into 10 into 10 into 10 into 10, that is 60,000. Now, the other side of exponent, negative power. We have already learned about the exponential, the quotient rule of exponent, which say a is to power m divided by a is to power n, that is equals to a is to power m minus n. This helps us to simplify division of the power of the same base. Here the base is same. We also explore the special case when m is equals to nm and nm equals to n, which led to use the zero exponent rule, a is to power 0, that is equals to 1. But what happened? The exponent in the determiner is larger than the exponent in the numerator, and that is when n is greater than m. This leads to negative exponent. When the exponent in denominator is greater than the exponent in numerator, in that case the exponent will be negative. Example, understanding negative exponent. Consider the expression 3 is to power 2 upon 3 is to power 5. We can solve in 2 ways. Method 1, expanding the power. So, that is equals to 1 upon 3 is to power 3. Second method, using the quotient rule. 3 is to power 2 upon 3 is to power 5, that is equals to 3 is to power 2 minus 5. So, that is equals to 3 is to power minus 3, 2 minus 5. Comparing the result with both methods, 3 is to power minus 3 equals to 1 upon 3 is to power 3. Negative exponent rule. A negative exponent does not mean the negative number. Instead, they indicate the reciprocal of the number. The general for any non-zero number and the positive integer a is to power minus m, that means 1 upon a is to power m, means it's reciprocal. The rule is also applied when the negative exponent appear in the denominator. One upon a is to power minus 1, so we can reciprocate it a is to power m and make it positive. Observation, negative exponent simply flip the base of its reciprocal and make the exponent positive. This rule works for any non-zero base and any integer exponent. Now, we will take an example here, evaluating expression with a negative exponent. If the exponent is negative, let us solve the following example. 4 is to minus 5 minus 3. Now, understand 4 is to minus 3. Negative exponent means we take the reciprocal of the base and then raise it to the positive exponent. So, that is equals to 1, reciprocal 1 upon 4 is to power 3. So we'll solve it 1 upon 64. Clear? Now note about the negative base. If the absolute value of exponent is even, the result is positive. If the absolute value is even, the result will be positive. If the absolute value of exponent is odd, the result will be negative. Minus 2 upon 5 is to power minus 2. So we'll reciprocate it to make the power positive because power is negative here. 25 upon 4. Clear? Now easy tips. A negative exponent means take the reciprocal of the base and use the positive exponent. For negative base, always check the absolute value of the exponent and determine the sign of result. Apply the result of the multiplication and exponent carefully after taking the reciprocal. Now, laws of exponent with a negative integer. The laws of exponent are the powerful tools to allow us to simplify expression without having to expand them fully. These laws are not only valid for positive exponent rule, product rule, quotient rule and the power rule. Can all be applied when the exponent are negative. Let's take an example here. Simplify the expression using the law of exponent. We have to simplify x is to power minus 2 upon and whole power 4. Solution, use the power of power rule. A is to power m into n a is to power m whole power n, that is equals to a is to power mn. So x is to power minus 2 multiplied by 4, that is equals to x is to power minus 2 into 4, that is minus 8. And we will reciprocate it 1 upon x to the power 8. So final answer 1 upon x to the power 8. This is how we are going to simplify. Now easy tips. Negative exponent means take the reciprocal of the base and use the positive exponent. Means first we have to reciprocate the base and that take positive exponent. Product rule, add exponent when multiplying powers are same. Quotient rule, subtract the exponent when dividing power of the same base. Power rules, multiply exponent when raising to the power of another power. The law apply even when exponents are negative. Next is learning point 2.2. Practice all the questions given here. You have to practice all these questions. Next is application of exponent. By now you are familiar with the law of exponent. These rules are in mathematical shortcuts allowing to simplify the long multiplication and division in just a few steps. One of the most important places where exponents are used in the real life, it is the working with the power of 10, especially exponent and power, because our number system is based on the decimal place value pattern. Now the power of 10. Have you ever thought about why 10 plays such an important role in the mathematics? Our decimal number system is built entirely around the power of 10. Each place value ones, tens and hundreds. Thousands are simplified, different power of 10. 10 is to power 0 means 1, 10 is to power 1 means 10, 10 is to power 2 means 100, 10 is to power 3 means 1000. This structure helps us to write very large or very small numbers in compact form. Expanded form using power of 10. You have previously learned how to expand the number like 6849, that is equal to 6000 plus 800 plus 40 plus 9. Using the exponent, we can write the more meaningful and organized way. 6 into 10 is to power 3 plus 8 into 10 is to power 2 plus 4 into 10 is to power 1 plus 9 into 10 is to power 0. This shows the where every digit of the number gets a value by multiplying the digit with a specific power of 10 based on its position. Now what about the decimal numbers? The idea of the power of 10 and work not only for the whole number but also for the number or with the digit after the decimal point. When we move to the right side of the decimal point, the power of 10 become negative. Because each place represents the part of the whole. Like 10th, that is equals to 10 is to power minus 1, 100 means 10 is to power minus 2, 1000 means 10 is to power minus 3. Let's take the number 317.46. So first we'll write in expanded form 300 plus 10 plus 7 plus 0.4 plus 0.06. Now rewrite each term using the power. So that is equals to 3 into 10 to the power 2 plus 1 into 10 to the power 1 plus 7 into 10 to the power 0 plus 4 because 0.4. So we'll write it 4 into 10 to the power minus 1 plus 6 into 10 to the power minus 2. This clearly shows the digit on the left on the decimal have the positive power and the digit at the right decimal they will have the negative power. Let's take an example, writing a number in the expanded form using the power of 10. Suppose we have to express this number using the power of 10. So solution, rewrite any number using the power of 10. We first look at the position of each digit from the left to right. From left to right, each place value corresponding to a specific power of 10. Let's break down the numbers. So the 7, 10,000 place, so which corresponded to 10 to the power 4. The digit at 5, that is 10 at 1000 place, that is 10 to the power 3. The digit at 6 at 100 place, so 10 to the power 2. A digit at 1 is 10th place, so 10 to the power 1. And digit at 8, that is at 1st place, so corresponding to 10 to the power 0. Now expressing the number by multiplying each digit with the matching power of 10, we'll write like this. Now expanded explanation. Each term represent the actual value contributing by the digit. 7 into 10 to the power 4, 70,000. 5 into 10 to the power 3, 5,000. 6 into 10 to the power 2, 600. 1 into 10 to the power 1, that is 10. 8 into 10 to the power 0, that is equals to 8. Adding them together, we will get the number. This clearly shows how the whole numbers is built from power of 10 and the value of digit. Now scientific notation. Have you ever tried writing extremely large numbers? For example, consider the approximate number of the stars of our galaxy is this, or the thickness of the strands of human hair, which is roughly around this. Now writing such numbers in full form is not only time consuming but also increase the chances of making mistakes that are very big or very small number. Even the single misplaced 0 can lead to the completely wrong answer in scientific calculation. To handle such values efficiently, scientists and mathematicians use a special method that is called scientific notation and known as standard form. Now what is scientific notation? Scientific notation allow to express very large and very small numbers in the compact and convenient form. In this format, any number is written as the product of a number between 1 and 10, that is called the coefficient. The power of 10 called the exponential part. In general form, it looks like a into 10 to the power n, where a is greater than 1 or equal to and less than 10. N is an integer, can be positive, negative or 0. Why do we use scientific notation? Now, why we use this method? It make calculation easier and cleaner. It reduce the chance of error when many zeros are involved. So, now what we will do? We will take an example here. Let's rewrite two numbers in the scientific notation. First, very large number. The distance from Earth to Sun is about this much. This is very large number. So, how we are going to write in scientific notation? 1.496 into 10 to the power 8 kilometer. Very small. The dust particle have the diameter, so we will write in scientific notation 5.1 into 10 to the power minus 6 kilometer. Now converting large number into scientific notation. How can we convert a large number into scientific notation? When we work on this very large number, writing all the digits can be inconvenient. Scientific notation help us to express such number in shorter, cleaner form. Here is a step to convert the large number to scientific notation. Step 1. Move the decimal point to the left. Move the decimal point left until only one non-zero digit remain before the decimal. The resulting value is called the coefficient. Step 2. Count how many places it moved to the decimal point, how many points left it shifted, count become the exponent of 10. Write a number in the form of a into 10 to the power 1, where a is greater than or equal to 1 or less than 10. N is the positive integer and large number. Here we will take an example. Express the approximate population of the fictional country in scientific notation. So, we have to express in the scientific notation. So, now what we are going to do? Move the decimal point so that the number become 6 point. Only one digit before. Will shift the decimal point to the left and only one digit before the decimal, 6.42. Now the decimal point move 9 places, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 places, and that become the exponent. So we'll write it 6.42 into 10 to the power 9. Now converting small number into scientific notation. Very small number, those that lie between 0 and 1, often contain several leading zeros after the decimal points. Then repeated can be slow and the error prone. Scientific notation help us to express these values quickly and accurately. To convert the small number into scientific form, follow 3 steps. Step 1. Move the decimal point to the right until it reaches first non-digit. The resulting value lies between 1 and 10 is called coefficient. Step 2. Count the number of places you move to the decimal point. The number become the exponent of 10. Write the number in the form of a into 10 to the power minus 9 here. The exponent is negative, showing that the original number was less than 1. We'll take an example here. The width of very thin fiber is given to us in meters. Write the value in scientific notation. So first we'll move decimal point, right, until the number become 6.3. So we'll move the decimal point to the right and the decimal point moves 6 places. That 6 become the exponent negative. So it will 6.3 into 10 is to power minus 6. That will be the answer. Now converting scientific notation to usual form. Now we know that to express the number in scientific notation, let us learn how to convert them back to their ordinary and usual form. The process depends entirely on the power of 10 expression. The value of the exponent tells us how many places the decimal point must move. The sign of the exponent tells us which direction the decimal point should move. Clear? Now step to convert scientific notation in a usual form. Write the coefficient, the number between 1 to 10. Identify the exponent of 10. Move the decimal point to the right if the exponent is positive and to the left if exponent is negative. Add zeros wherever necessary to complete the movement. Let's take an example here. The estimated distance between the distance of star 2.73 into 10 to the power 9 km. Now we have to express it in usual form. Here the coefficient is 2.73, exponent is positive 9. Means move the decimal to the 9. Place to the right. Start from 2.73. Move 2 places. Now add the remaining 7 zeros. So this will be our answer. Clear? Practice all the examples. Next is working with scientific notation. After learning how to express number using scientific notation, it becomes important to understand how to compare, multiply and divide written in the form. These operations allowed us to handle the extremely large or very tiny measurement such as the width of the virus of the brightness of the star without writing long string of digits. Now comparing values written in scientific notation. Suppose we want to determine whether 4.2 into 10 is to power minus 29 kg is greater smaller than 7.5 into 10 is to power minus 25 kg. To compare these numbers, we convert them so that they both share the same exponent. When the power of 10 is equal, comparison becomes simple. We only look at the coefficient. So step to compare scientific notation numbers. Step, adjust the exponent. Identify the number with the more negative exponent. This represents the smaller magnitude. More negative. Move to the decimal point to the left until both numbers have the same power of 10. Every step, so we have to make the power same. Every step you move to the decimal left, increase the exponent by 1. Step 2. Compare coefficient. Once the power of 10 matches, compare only the decimal numbers, the coefficient. The number with the greater coefficient is larger place value. Clear? Now, example, which particles have the more mass? The certain nanoscale particle have the mass of 4.2 into 10 to the power 29 kg and the microfragment have the mass of 7.5 into 10 to the power 25 kg. Which one is heavier? Solution, first we will rewrite the mass with the smaller exponent so that its exponent matches with the larger one. 4.2 into 10 to the power 29. To convert the exponent minus 29 to minus 25, will increase it by 4 because we have to convert it to minus 25. So, we will move the decimal point 4 places left. 4.2 into 10 to the power 29, that will become this. Now, we will make the exponent same. Now, the comparison between the mass of the nanoscale particle, this, and the mass of the microfragment. So, we can easily find out 7.5 is greater than 0.00042, means the microfragment is much heavier than the nanoparticle. Now, multiplication and division of scientific notation. Scientific notation help us to express extremely large or very small numbers in the compact way. One of the biggest advantage of it make multiplication and division much simpler by applying the laws of exponent, multiplying the number in the scientific notation. Step 1, multiply the coefficient, carry out the usual multiplication with the decimal number, add the exponent, use the law of exponent, 10 to the power 8 multiplied by 10 to the power b, that is equals to 10 to the power 8 plus b. This means simply add the exponent of 2 powers of 10. After combining the coefficient and the new exponent, make sure that the final answer in the proper scientific notation, coefficient between 1 to 10. Let's take an example here, distance travelled by the fast moving object. Problem, a spacecraft cruises through the space of speed 4.8 into 10 to the power 7 meter per second and travels for 2.2 into 10 to the power 6 seconds. Approximately how far does the travel in that time? Solution, we need to multiply the two numbers, 4.8 into 10 to the power 7 multiplied 2.2 into 10 to the power 6. So, first we multiply the coefficient, that is equals to 10.56, then we will add the powers, that is equals to 10 to the power 13. So, combining result 10.56 into 10 to the power 13. This is not yet standard scientific notation because the coefficient must be between 1 and 10. Move the coefficient to 1 place left. So, that is equals to 1.056 into 10 to the power 14. So, final answer is this. Now, dividing the number in the scientific notation. Division of scientific notation follow the same idea of the multiplication but with one important difference. Instead of adding exponent, we subtract them. This makes division very large or very small number much easier. Step 4, dividing numbers in the scientific notation. Step 1, divide the coefficient. First, we will divide the coefficient, perform the normal division using the decimal numbers. Now, step 2, subtract the exponent. Apply the quotient rule of exponent 10 to the power 8 divided by 10 to the power b, that is equals to 10 to the power a minus b. This means we subtract the exponent of the division from the exponent of dividend. After both steps, adjust the result if necessary to make sure the coefficient is between 1 to 10. Let's take an example here comparing the mass of two moons. So the large moon have mass of 9.0 into 10 to the power 23 kg, while the smaller moon have the mass of 3.6 into 10 to the power 21 kg. How many times heavier is the larger moon compared to the smaller one? So we'll divide the two quantities. First we'll divide the coefficient, that is equals to 2.5. Now we'll subtract the exponent. 10 to the power 23 minus 21, 10 to the power 2. So final answer is 2.5 into 10 to the power 2. So the larger moon is 2.5 into 10 to the power 2 times heavier than the smaller moon. Now estimation and approximation. Understanding the law of exponent give us the power to calculate the exact value, but mathematics is equally valuable when we need to quick and reasonable answer, especially in the real life situation where the perfect accuracy is unnecessary. This is where the idea of estimation and approximation play an important role. Why estimation matter? In many day-to-day scenario, we cannot or do not need to find the exact figure. For example, approximately how many plastic bottles could fit your school bus? Roughly how many breaths do you take in one day? To answer such questions, we make educated guess based on the logic and simple assumption. Professionals in the field such as construction, medicine, space, science, economics and the disaster management regularly use these skills to make quick decisions. Steps involved in good estimation. Step 1. Make an initial guess. Before calculating anything, think about what the answer might be based on your existing knowledge. Step 2. Break the situation into smaller parts, dividing the big question into several simple questions. Make it easier to handle. Step 3. Assign reasonable approximate value. Exact value are not required. Choose a number that are easy to work with and close to reality. Calculate the based on your estimate. Use the estimated value to get an approximate answer. At the end, see whether the result seems reasonable compared to your initial guess. Let's take an example here. Estimate the number of ₹2 coin required to reach the height of the Charminar. Now problem. You have to estimate the number of ₹2 coins to reach the height of Charminar. So about how many ₹2 coin must be stacked one over another to reach the height of the historical Charminar? Assumption using the change number, approximate height of the Charminar, that is approximate height 55 meter. Approximate thickness of ₹2 coin, that is 3 mm. Now convert the height in millimeter, so that is equals to 55,000 millimeter. Now divide the total height by the thickness of the coin, so that is equals to 18,333. Now write the scientific notation, that is equals to 1.83 into 10 to the power 4. Now estimated answer, approximately 18,000 coins or 1.83 into 10 to the power 4 coins needed to reach the height of Charminar. Now linear versus exponential growth. To understand the difference between the linear and exponential growth, imagine how different situation where the creator to trying to increase the number or follower to new learning platform over 12 days. The regular boost, linear growth. Suppose you place a study online promotion that gives you 800 new followers each day. No increase, no decrease, just the same amount daily. So day 1 800, day 2 800 plus 800 1600, day 3 2400. So continuing this pattern, day 12 12 into 800, 9,600 followers. Journal expressions. If you count the number of days as n, then the followers 800 into n. This is linear growth. The total increase by the constant amount every single day. The graph of this type growth form a straight line. Now scenario 2. The exploding trend, exponential growth. Now imagine you upload a brilliant educational reel that starts spreading rapidly. The number of views triples every day and begin with 3 views on first day. So start with the 3 views on the first day, day 2 9 views, day 3 9 into 3 27, and day 4 27 into 3, that is 81, 3 is to power 4. Now continuing, day 10 59,049 views, day 15 3 is to power 15, this much views. So this is exponential growth. Here you can see the growth is exponential. The quantity is multiplied by the constant factor each day. It begins slowly, but after a few steps the number increases dramatically and soon exceed linear growth by the huge margin. Why exponential growth become powerful? Linear growth adds, exponential growth multiples. So in linear growth it just add every time, but in exponential growth it get multiplied. The simple rule: in the beginning exponential growth looks small, but after some time it become massive. The real life connection, compound interest. So a strong example of exponential growth in real life is compound interest. While the simple interest increase by the fixed amount each period, the compound interest increase by the percentage of the total amount. We know the difference between the simple interest and compound interest. So in compound interest it increase by the percentage of total amount, causing the amount to grow faster and faster, just like the exponential growth. Ancient India texts recognize the principles, early economics writings and those from time of the Kautilya explain the rules of lending. From the time of the Kautilya explain the rule of lending and interest. The idea was clear even then. When interest is added back to the original amount, the money grows at an accelerating rate. This is the same phenomena used today in the saving accounts, investment and the population studies. Next is quantifying the world with the powers. Scientific notation is not only the tool for the performing calculation, it is an essential language for describing the enormous range of sizes and the quantities that exist in our universe. From tiny microorganism to giant celestial structure, power of 10 help us clearly express the value that are far too large, too small to write in ordinary form. Understanding scale through scientific notation. The world around us includes numbers. We can see numbers everywhere that vary by unimaginable amount. By using powers of 10, we can compare them easily and understand how vast or how tiny different quantities truly are. Below are explained the table showing a variety of natural and global quantities rewritten in the new examples and modified values expressed in scientific notation. So here we'll see the table. Scale of natural and the universal using power of 10. Here you can see the table, scale of nature and the universal using the power of 10. So here you can see the power of 10. 10 is to power 0 mean 1. 4 into 10 is to power 0 means 4. Now 10 is to power 2 means hundreds, 10 is to power 5 means lakhs means 100,000, 10 is to power 6 means millions, 10 to the power 9 billions, like this. Here the power of 10 is given, you can see how it increased. So this is the complete table where you can see the power of 10. Next is, why this better? Using scientific notation. So we have learned about the scientific notation earlier. Let us compare quantities that differ by thousands, millions and even trillions of times. Help scientists record information clearly and avoid long, hard to read numbers. Make global data such as population studies, astronomy and environmental science easy to interpret. Scientific notation is the universal tool that allows us to describe the world accurately and efficiently regardless to scale. So scientific notation make our task easier. We can write large number or even very small number very accurately using scientific notation. The scale of time, just like the distance and the quantities, time also cover the enormous range. From the blink of an eye, the age of our plant. Power of 10 and offer a simple way to understand the time interval that are otherwise too huge to imagine. The table below use the power of 10 to show how small and large different time spans can be along with the completely new real world comparison. Time in second using power of 10. So here you can see time is expressed using power of 10. 10 to the power 0 second means 1 second time taken to blink once. 10 to the power 2 second, 10 to the power 4, 10 to the power 5 seconds. So here the second is used, second is expressed using the power of 10. You can see the table. Next, understanding approximately equal to. The symbol means this value is close to the actual number but not exact. So this is close to the actual value but not the exact value. We use it when a number is rounded. The exact value is difficult to determine. We are estimating extremely large quantities. Scientific and historian frequently use this symbol because some values like the age of the fossils, planet and the ancient event cannot be known with the 100% precision. Naming large numbers. So for centuries, different civilizations tried to find ways to name enormous number that exceed everyday experience. Various cultures grouped large values differently. Some grouped digits set of 3, 1000, million, billion and trillion. Other grouped number in the sets of 2 like lakhs and crores in the Indian system. These systems helped humans to organize and growing complexity of astronomy, trade, mathematics and record keeping as numbers stretch far beyond the normal comprehension. Now we will understand the architecture of the large number. How do you name the number with 15 or 30? Humanity's answer to this challenge was to create architecture for the number system, systematic ways of grouping them. While all modern systems rely on the power of 10, the way they group the powers led to the different names for the same vast quantities. Let's explore the two most prominent systems. So first is the Indian system, an architect power of 100. So this system used across the Indian subcontinent. So this system is used in Indian subcontinent, used unique base terms like lakhs and kotis and also known as crores. Beyond the koti, the system traditionally progressed by multiplying by 100 or 10 to the power 2. Now, 100 koti, that is equals to 1 arab. 100 arab, that is equals to 1 kharab. 100 kharab, that is equals to 1 nil, and 1 nil, that is equals to 1 padma. 100 Padma, that is equals to 1 Shankha, and 100 Shankha, that is equals to 1 Mahashankha. Now the international system, an architect of the power of 1000. The globally accepted system works by the groupings in power of 1000, which is why the commas are placed every 3 digit. This system uses Latin prefixes and the signs, signals and the magnitude, making it predictable. Name the power of 10 logic in the prefixes. So, the base is Latin root. Million, 10 to the power 6, base unit. Billion, 10 to the power 9. Trillion, 10 to the power 12. Quadrillion, 10 to the power 15. Quintillion, 10 to the power 18. Sextillion, 10 to the power 21. Then septillion, 10 to the power 24. Octillion, 10 to the power 27. Nonillion, 10 to the power 30, and decillion, that is 10 to the power 33. Now, here we will take an example here. The large Indian company market valuation is reported to be 80,000 crore rupees. Express this value in scientific notation. So, the solution 80,000 crore. So, we will write like this. So, now we will express in the power of 10. So, 8, this can be written as 10 to the power 3 and this can be written as 10 to the power 7. Clear? Now, we have to write in scientific notation. So, we will shift the decimal to the left. So, that is equals to 8.0 into 10 to the power 11. 7 plus 3, 10 and 1. 10 to the power 11. Hence, the company's valuation is 8.0 into 10 to the power 11. Now, large numbers. The Indian numbering system, grouping by the power of 100. The Indian system, widely used across the subcontinent, has unique base terms such as the lakhs, crores, and beyond crores. The systematic traditionally progress by multiplying by 100 for each successive tier. Here you can see every time we are multiplying by 10 to move the next number. Each term in this system represent a power of 100 compared to the previous term, making it convenient for grouping very large amounts such as the national budget or corporate valuation. The international numbering system, grouping by power of 1000. So, globally numbers are typically grouped in the power of 1000. Commas are placed after every 3 digits. The Latin prefixes indicate the magnitude to make the system predictable and systematic. Here you can see the table. Every time we are moving, if we are coming down in the table, the value increased by 1000. Clear? Million, billion, trillion. So, value is increased by 1000. This system is widely used in scientific research, finance and the astronomy because the progression is consistent and easy to predict. Example, expressing the large Indian company's market value. So, the problem, first we will take the problem. A company's market value is reported as 50,000 crore rupees. Express the number in scientific notation. Solution, it break down 50,000 crore. 50 into 1000 into crore. So, convert each part to power of 10. So, 50 into 10 to the power 3 into 10 to the power 7. Scientific notation we have to write. So, express 50 as 5. So, 5 into 10 to the power 1. So, total 7 plus 3, 10, 1, 11. Clear? This is how we are going to write, like at the exponent 5 10 to the power 11. So, market value approximately 5 into 10 to the power 11 rupees. This is example shows how the Indian numbering system can easily be converted into the scientific notation for the precise calculation and global understanding. Next is learning point 2.3. So, all these questions are based on the concept we have done in the chapter. So, you have practiced all the questions. Next is summary. Exponent definition. An exponent indicates how many times a number is multiplied by itself. Example, 2 into 2 into 2 into 2, that is 8. Base and power in A. A is the base and A is to power n. A is the base and n is the exponent to power. Laws of exponent. A perfect square always ends with 0, 1, 4, 5 and 6. Product rule. A is to power m into A is to power n, that is equals to A is to power m plus n. Power of power, A is to power m whole power n, so A is to power mn. 0 exponent, A is to power 0 means 1. For A is not equals to 0. Quotient rule, A is to power m divided by A is to power n, that is equals to A is to power m minus n. So power of product AB whole power n equals to A is to power n, B is to power n. Negative exponent, A is to power minus 1, that is equals to 1 upon A. Counting combination using exponent. If there are m choices and one thing and n for another, so total combination m into n. Negative power represent reciprocal of the number. Example, 2 is to power minus 3 equals to 1 upon 2 is to power 3, that is 1 by 8. Application of exponent. Population growth, compound interest, area, volume calculation, computing large and small quantities. Next is estimation and approximation. Useful when the exact number are unnecessary. Steps: make the guess, divide the problem into smaller part, estimate, calculate. Scientific notation or power of 10. Express every large number or very small number conveniently. For example, here you can see we can express this number like this, 3.210 and 5 into 106, like this we can express. So we can express very large number, very small number very conveniently using scientific notation. Next is quantifying real world problem. Distance in space, population, bacteria or atomic size can be expressed using power of 10. Next is linear versus exponential growth. Linear increase by the fixed amount and exponential multiply previous value by the constant factor grows faster over time. Combining exponent in real life problem. Example, population doubling, viral content, bacterial growth or sticking object. Estimating large numbers. Break numbers into powers of 10 and make the calculation easier. Order of magnitude. Help compare very large and very small number by rounding to nearest power 10. Powers in daily life. Computer storage. Like bytes, kilobytes, megabyte, gigabyte. Earth's population, scientific measurement, finance. Exponent simplify calculation. Multiplication, division and repeated operation become simple using exponent rule. So this exercise you have to practice all the question. Here we end the chapter. In this chapter we have learned about the exponent, the rules where the exponent are used in real life, what are the laws of exponent, all this we have learned in this chapter. I hope all these things are clear to you. Now to practice it.